Next, we will discuss the color coding technique. Let's look at an example. Longest path. The input is a graph G and an integer k, the parameter is k, and the question is whether G has a path on k vertices as a subgraph. So it must be possible to find some path on k vertices in our graph, but of course this doesn't need to be an induced subgraph. So we could have additional edges here, and of course additional vertices. Okay, well, this is an NP-hard problem, and one can easily show this by reducing from the Hamiltonian path problem by setting k equals to n and leaving the graph unchanged. The following lemma is crucial for the color coding technique. So by this bracket notation here, I denote the set of integers from 1 to k. So what we are going to do is, well, we are looking at a set U of n elements. And so let's say that we want to find a set X of k elements inside the bigger set U on n elements. So U could be our vertex set, and X could be the vertices of the path that we want to find. We are now going to color the elements of U with colors from 1 to k. And we are going to choose this coloring uniformly at random. So every element of U gets a random color between 1 and k. So we now want to know what is the probability that, well, the set X here has k different colors. So X has size exactly k, and we also have k colors. So we want to lower bound the probability that actually in X we have k different colors. And this lemma lower bounds this probability by e to the power minus k. So to lower bound this probability, we are going to try and figure out what fraction of all colorings have this property. So in total there's k to the n possible colorings of n elements with k colors. Now the question is, how many of them give distinct colors to the elements of X? So in other words, how many of them are injective on X? So if we look at the k elements of X, we could color them with 1, 2, 3 up to k, or with 2, 1, 3 up to k, or we could start with the color k and then have k minus 3, and then have 1, etc. Maybe we end with 2. But so any permutation of the colors 1 to k works for the elements of X. For the elements outside of X, we don't have any constraint, any coloring works. So for those vertices, or for those elements inside X, we have k factorial possibilities, and for those outside of X, we have all the possible colorings, which is k to the power n minus k possibilities. So now we use the inequality that k factorial is more than k divided by e to the power k. And this comes from Stirling's approximation. So let's see. So Stirling's approximation says that here k factorial is more or less some factor, which is positive, times k divided by e to the power k. Let's also check whether this actually makes sense, just as a sanity check. So let's draw the two functions. One is the factorial of x, and the other one is the x divided by e to the power x. And we'll go from 0 to 7. Yep, it looks that this is sensible. The factorial goes quicker than x divided by e to the power x. Okay, and now we can already conclude because, well, if we look at the number of colorings that have the property that we want, and we divide it by the total number of colorings, then what we get here is we have k to the power n minus k divided by k to the power n, so this stays, and k factorial is more than k divided by e to the power k, so you get this here. Okay, so on the top we have k to the power k times k to the power n minus k, which in total is k to the power n, and so this simplifies, and we just get 1 divided by e to the k, which is e to the power minus k. Okay, so if we now think of u as the vertex set and of x as the vertices of our path, then this lemma tells us that if we randomly color the vertex set with k colors, then with probability e to the power minus k, we get that well, the path we are looking for has vertices with k different colors. We're not done yet, but at least this helps us. Okay, so we're going to randomly color the vertices of the graph, and now we want to check whether there's a colorful path. And so a path is colorful if all vertices have different colors. So, okay, so we need to find, well, we need an algorithm that actually checks whether a colored graph has a colorful path. So, and we can do this in time O star of 2 to the power k by the following algorithm. We partition the vertex set into its color classes. So we have the vertices with color 1, those with color 2, etc., up to vertices with color k. Actually, let me first show you a simpler but slower algorithm. So let's say we go through all k factorial orderings of the color classes. And let's order them in some way. Let's say 1, 2, 3 up to k is the ordering that you have chosen. So now the question is whether there's a path from a vertex in v1 to a vertex in v2 to a vertex in v3, etc., to a vertex in vk. So let's say we delete all the edges that are within v1 and also that don't go across two consecutive color classes. So we'll just delete all the edges that don't work for us. And then, well, the only thing we need to do is, well, check whether there's two vertices, well, one in v1 and the other one in vk, that are connected. Because if they're connected, then there exists a path that follows exactly the way that we imposed by deleting those edges that we are not allowed to use. But there exists actually a faster algorithm, and this is by dynamic programming. So we will say that, so this is the values that we will compute. So, and it contains, well, a set of colors S, that's a subset of 1 to k, and we have a vertex U. So, and this value here is 1 if there is a colorful path with colors from S and U as an endpoint. So in that case, there's some path with cardinality of S many vertices, and U is one of the degree 1 vertices of this path. Okay, so these are the things that we want to compute, and we want to build it up from small s to large S. now we have the following recurrences. So if the size of S equals 1, then PSU is equal to 1 only if the unique color of S is U's color. And PSU is 0 otherwise. So now if S is larger, then PSU is equal to 0 if the color of U doesn't even occur in S. And if the color of U occurs in S, then what do we have? So we have that U must be an endpoint of a path. And the remaining path, well, it cannot be colored with U's color, so we remove the color of U. And it must end in some vertex that's a neighbor of U, and it must use up the remaining colors. So we have a big OR over all the edges between U and some vertex V. And now we need to have a path that covers all the remaining colors that ends in V. Okay, and so all of these values of P can be computed in O star of 2 to the power k time, because, well, we just need to compute it for every set of colors, and we have k colors, so there's 2 to the power k choices, and every vertex, but there's only n vertices, so that's a polynomial factor. Okay, so all of these values can be computed in O star 2 to the power k time, and now there exists a colorful k path if and only if P of, well, the set from 1 to k, comma V is equal to 1 for some vertex V. So now that we can check whether a colored graph has a colorful path in time O star of 2 to the power k, so the Monte Carlo algorithm with one-sided error that computes a random coloring and then checks whether there's a colorful path, takes time O star of 2 to the power k, and it has success probability e to the power minus k. So we are going to run this algorithm, the inverse of the success probability many times, in order to get constant success probability. And to get a randomized algorithm with constant success probability with running time O star of 2 times e to the power k. And so notice that the color coding technique can be applied whenever we are looking for a subgraph of size f of k with constant tree width. Next, we will talk about monotone local search. Let me first give you a bit of history. If we look at a problem such as feedback vertex set, then the two most common parameters are n, the number of vertices, and k, the size of the solution. So the size of the feedback vertex set that we want to find. So now suppose that we have made a lot of progress in terms of k. So we have designed faster and faster algorithms where we optimized and analyzed the running time in terms of k. Now the question is, can we somehow use this progress in order to also design faster exponential time algorithms? So suppose that we have a very fast parameterized algorithm. Does this imply that we also have a kind of fast exponential time algorithm? And let's focus specifically on feedback vertex set for now. So in terms of n, there's of course the trivial brute force algorithm that runs in time O star of 2 to the power n. And for a long time it wasn't clear whether this can be improved at all. In 2006, Igor Rascon made the first breakthrough and gave a faster algorithm than 2 to the power n. And there was a slight modification of the algorithm, and these two papers got then combined into a joint journal version here in 2008 that gave a 1.7548 to the power n time algorithm. And there have been a few improvements since then, but nothing dramatic. Now, in terms of k, it started off very slowly, So with a slow FPT algorithm, but nevertheless, so this was a big deal because the problem was FPT, which got improved, and now the fastest randomized algorithm is this one, and there are also deterministic algorithms that are very competitive. So now the question is, can we somehow use this result here, the 2.7 to the power k algorithm, in order to get an improved exponential time algorithm? Let us think a bit more generally about the following question. When does a good running time in terms of k imply a good running time in terms of n? So for feedback vertex set, we know that we have a running time in terms of k of O star of 2.7 to the power k. Let's assume that k is at most n, because otherwise we can easily solve the problem. So since k is at most n, this now implies a running time of O star of 2.7 to the power n. But of course, this is not very interesting because we have a much faster algorithm already. So we can now think about, okay, maybe it makes only sense to run the parameterized algorithm when k is small. So maybe we say that if k is at most 0.6 times n, then we run the parameterized algorithm, and then it has running time O star of 2.7 to the power 0.6 times n. I'm pretty sure that 2.7 to the power 0.6 is less than 2. So this is good. But now what if k is more than 0.6 times n? Then we just do the brute force algorithm. So we just do an n choose k time brute force search. And so why do we think that this is nice? Well, this is nice because, well, if we look at n choose k, then the worst case, so the maximum running time that we get, is when k is equal to n half. And if k is equal to n half, then we have that the running time is roughly 2 to the power n divided by square root of n. But when k is bounded away from the middle, the running time should drop. So let's quickly check this. So let's draw values of the binomial coefficient. Let's say n is 100 and k is anything between 0 and 100. And so these are integer values, so I'll have to do a list plot. Yes. So we can see here that towards the middle here, when k is about 50, then, well, the value of the binomial coefficient is much larger than when it's 60, for example. Maybe we can draw this on log scale as well to see a bit more detail. And I want only the y-axis to be log scale. Yeah, so this is how it looks on the log scale axis. Okay, so we think now that it makes sense to try and bound k away from 0.5 n. And so we basically need to do something different in that middle range where k is close to 0.5 times n. So the parameterized algorithm will allow us probably to go beyond 0.5 times n. So like we let k range from 0 to 0.6 times n, and in that case we run the parameterized algorithm, and if k is larger than that, we do a brute force search. Okay, so our algorithm is now the following. So we select some threshold t, which is maybe not 0.6 times n, but 0.6511 times n. Now, if k is at most t, we run the parameterized algorithm. Otherwise, we check all k-sized subsets of the vertex set and to check whether that's a feedback vertex set. So now the final running time is, well, the maximum of the two. So it's maximum among 2.7 to the power t and n choose t. So how have we selected this value t? Well, we solve the equation 2.7 to the power t is equal to n choose t. So when are those two equal? Well, for n choose t, we will use Stirling's approximation. So n choose t is n factorial divided by t factorial times n minus t factorial. So, and we don't care about polynomial factors here. So we just say that, so this is more or less n divided by e to the power n divided by t divided by e to the power t times n minus t divided by e to the power n minus t. So now, if we look at this factor 1 divided by e, how many times it occurs? So 1 divided by e is raised to the power n on the top. And so here on the bottom we have 1 divided by t to the power t times 1 divided by e to the power n minus t. So on the bottom it occurs t plus n minus t, so n many times, and at the top we also have 1 divided by e n many times. So we can just simplify this. So now we have that this is equal to n to the power n divided by t to the power t. And actually I'll split up n. I'll say, okay, n appears t times over here and n minus t times over here. So here we have n divided by n minus t and all of it to the power n minus t. So now I can actually, well, get rid of my variable n here. Because, well, what do I have here? So I can just say maybe t is equal to, so tau times n. So tau would be this value here that we are looking for. That's what we want to find out. Now we can say, okay, so we want that, so 2.7 to the power tau times n is equal to, and now, well, I have n on the top and tau times n on the bottom, so I can simplify by n, and this becomes 1 divided by tau. To the power t, which is tau times n. Okay, times, and here I'll do the same. So it's 1 divided by 1 minus tau to the power n minus tau times n, so it's 1 minus tau times n. Now I can just get rid of n here. Okay, so I need that 2.7 to the power tau is equal to 1 divided by tau to the power tau times 1 divided by 1 minus tau to the power 1 minus tau. And this is something that we can solve now. So let's see if we can solve it. So let's try and solve 2.7 to the power, I'll use t instead of tau. So this is equal to, that was 1 divided by, let's use x instead of t. otherwise I need to define a new variable. 1 divided by x to the power x times 1 divided by 1 minus x to the power 1 minus x. And I assume that we can't solve this as is. Yeah, it's not able to solve it, so we'll need to do a numerical approximation. So we're going to try and find a root that's in between. So x shouldn't be 0, so let's say it's in between 0.01 and 1. Okay, so we indeed find 0.6511 something. And now, if we want to know the actual running time, we can just compute 2.7 to the power of, well, the answer that we got here. And we'll truncate it to the 4th digit, because that's what our algorithm says. And then we get 1.9093 to the power n as a running time. Because, so if we don't plug in this exact number, and it's probably an approximation anyway, then we have to round it up in order for our analysis to be correct. So we will not be able to say that we have a 1.9092 to the power n algorithm, because that wouldn't be correct. If you want to give a valid upper bound on the running time, we have to always round it upwards. Okay, so we'll now indeed get this running time here. So we'll have a running time of O star of 1.9093 to the power n. So this is just by running the parameterized algorithm when k is small, and otherwise doing an exhaustive search. And so this is, of course, a very general technique. And so this approach gives an algorithm that's faster than 2 to the n for such subset problems where we want to find, let's say, a subset of vertices among a set of n vertices, or maybe a subset of edges or a subset of variables, etc. So it works for subset problems that have a parameterized algorithm that's faster than 4 to the power k. Because indeed, once we are at 4 to the power k, so we'll be solving 4 to the power t is equal to n choose t. And so this would then solve to t is equal to 1/2. Because, well, 4 to the power 1/2 is 2, and here we also get n choose n/2, which is also roughly 2 to the power n. But as soon as we have an algorithm that's faster than 4 to the power k, we get a better exponential time running time. Okay, so that looks nice. But we actually want to do better than this. So because the fastest known algorithms had running times that were 1.7 something to the power n. So and this is where monotone local search comes in. And so I define it more generally, not just for feedback vertex set, but for subset problems in general. So and for this, let me introduce implicit set systems. So, and an implicit set system is just a function that we are not necessarily going to evaluate, but it's a function that we are going to work with. So the input to the function is an instance I, and we just say that the size of I is equal to capital N. And now, so this could be our input to the problem, such as a graph and an integer k. Now, the output is a set system consisting of a universe and a family of subsets of the universe. So this is what will define the subsets that we are looking for when we are solving a subset problem. So and the universe is some set of size n, small n, and the family of subsets is, well, the family Fi consists of subsets of the universe. So if we're talking about feedback vertex set as an example, so in feedback vertex set, we would have that Ui is, well, the vertex set of our graph. And what would Fi be? So Fi would be actually what we want to find. So what do we want to find? We want to find feedback vertex sets of size at most k. So this is the set of all feedback vertex sets of size at most k. And okay, if we're just talking about decision problems now, in a decision problem, we are just interested in whether this family is non-empty, so whether there exists a solution. If we're talking about optimization problems, we might want to find an element of F, of this family F. Or if we talk about enumeration problems, we might want to enumerate everything that's in F. Okay, yeah, so the phi subset problem, where phi is an implicit set system, is just, well, the input is an instance I, and the question is whether the family is non-empty. Now, there's another important problem. Suppose that, well, we want to solve our subset problem, but we have already selected some elements of the universe and said, okay, these will be in our solution. Then the question will be, well, can we extend this set of elements to an actual solution that occurs in our family? So the extension problem is the following. The input is an instance and also a set of pre-selected elements of the universe and also an integer k. The question is whether there exists a subset of the universe minus the pre-selected elements, such that, well, if we add this subset to the pre-selected elements, we get a set in our family F. And this subset S must have size at most k. The question is, well, given this pre-selected set of elements, can we add another k elements such that we actually get something that we're interested in, so some set in our family. So in terms of feedback vertex set, this would be, well, given a set of vertices that we have already selected and an integer k, can you add k more vertices to the pre-selected vertices such that we actually get a feedback vertex set of a certain size. Okay, now assume that this extension problem has a c to the power k time algorithm. Now, this is the algorithm that I'm proposing. We again select some threshold, which depends on c, on k, and on the universe size n. And now we uniformly at random select a subset of the universe of size t. And then, well, we won the algorithm for the extension problem. So the subset that we have randomly selected is our pre-selected elements. And now we are going to try and see whether there's an actual solution of size k minus t. And I've selected this threshold here in some way. And I made sure that it's non-negative. So this is now a randomized algorithm, and it has some success probability, and we are going to repeat it a number of times in order to get constant success probability. So what's the running time that we get in the end? So of course, so for the second part, where we run this c to the power k algorithm, where the parameter is now k minus t, so we get the factor c to the power k minus t. And so how many times do we run this algorithm? Well, it's the inverse of the success probability. So what's the success probability? Well, suppose that, well, we have a yes instance. If we have no instance, then we have success probability 1. But suppose that we have a yes instance. Then, well, there exists a solution of size k. So this algorithm is for checking whether f contains a solution of size k. So if it contains such a solution, size k, and our t elements that we have selected are a subset of that solution, then we will find the solution for sure. Okay, so the number of valid choices are at least k choose t. Now the total number of choices are, well, n choose t, because we select any subset of size t among a universe of size n. So the total number of choices is n divided by t. So the success probability is k choose t divided by n choose t. And we take the inverse, of course, for our running time, and so we get a running time that's O star of n choose t divided by k choose t times c to the power k minus t. And it turns out that, well, we can, well, simplify this and write it as O star of 2 minus 1 on c to the power n. The details are quite tedious, and you can find them in this paper. Okay, so now with the simple algorithm here, we immediately get a running time that's O star of 2 minus 1 on c to the power n. So with our previous technique, we had a bottleneck when we only had a 4 to the power k time algorithm. But now, well, if we have a 4 to the power k time algorithm for the extension problem, then we get a 2 minus 1 on 4 to the power n time algorithm. So, and that's of course 1.75 to the power n. So we can view this algorithm as picking elements of the universe uniformly at random, one by one. And at some point it stops and it runs the parameterized algorithm whose running time depends on k. Or k minus the number of elements that we have already selected. Okay, so initially, suppose that k is large compared to n. So initially, we have quite high probability of making no mistakes. So initially, we have high success probability if k is large compared to n, because, well, it suffices to find a vertex among k vertices. And the total number of choices is among n vertices. So with probability k divided by n, we don't make a mistake when choosing the first vertex. But then once we have chosen the first vertex, well, the probabilities keep decreasing, right? So for the second vertex, we have k minus 1 valid choices among n minus 1 possible choices. And then we have k minus 2 valid choices among n minus 2 possible choices. So and we see that this ratio here, it keeps decreasing. So at some point it will be just 1 divided by some large number. And then it's of course not interesting anymore to do random choices. So at some point, for some t, it will be the case that k minus t divided by n minus t is more or less equal to 1 on c. And 1 on c is significant because, well, c is the base of the running time of the parameterized algorithm. And So if k minus t divided by n minus t is equal to 1 minus c, we have that, well, the inverse of this success probability here is n minus t divided by k minus t is equal to c. And so the inverse of the success probability, of course, tells us how many times we have to repeat this algorithm. And if this becomes equal to c, then it doesn't pay off anymore to do random choices. We are better off than using the c to the power k time algorithm. Then solving this here gives us an indication where this threshold value here comes from. So now we have the result that if there exists an algorithm or randomized algorithm for the phi extension problem with running time O star of c to the power k time, then there exists a randomized algorithm for the phi subset problem with running time 2 minus 1 on c to the power n time times a polynomial in the instance size. Okay, so what does this imply for feedback vertex set? Well, for feedback vertex set, what is the phi extension problem? What is the feedback vertex set extension problem? So the feedback vertex set extension problem is, well, given a graph and a set of pre-selected vertices that we have to put into the feedback vertex set and an integer k, can we put k more vertices into our feedback vertex set such that, well, we get a feedback vertex set. Okay, but for those pre-selected vertices, we know that, well, you can just remove these vertices from the graph. We know that, well, if we remove these vertices from the graph, and for the resulting graph we just look for a feedback vertex set of size k, then we solve this extension problem. So basically the extension problem is more or less the same as the feedback vertex set problem. So for feedback vertex set extension, we also have a 2.7 to the power k time algorithm, and that's why feedback vertex set now has a randomized algorithm with running time 2 minus 1 divided by 2.7 to the power n, and this is a most order 1.6297 to the power n. So this is a big speed up. And so if we're not happy with randomized algorithms, there is a way to de-randomize this algorithm. So we can de-randomize the algorithm at the expense of a sub-exponential factor in the running time. So now we can say that if there exists a deterministic algorithm, so a non-randomized algorithm for phi extension with running time c to the k, then there exists a non-randomized algorithm, so a deterministic algorithm for phi subset with running time 2 minus 1 on c to the power n plus little o of n. So meaning that we will have some sub-exponential factor as well in our running time. Okay, so if we use the best deterministic algorithm for finding feedback vertex sets of size k, then this will now lead to a running time of 1.7110 to the power n. So notice that there doesn't seem to be a sub-exponential factor, but this is because, well, these numbers here were rounded upwards, and so any exponential factor in the big O notation will basically eat up all the sub-exponential factors. Okay, and you can read more about randomized algorithms in chapter 5 in the Parameterized Algorithms book, and also in the paper Exact Algorithms via Monotone Local Search. These are the references, and that's it for today.